So, virtual memory. So, the memory management algorithms outlined in Chapter 8 are necessary because of one basic requirements. So, the instruction being executed must be in physical memory. So, the first approach to meeting this requirement is to place the entire logical address space in physical memory. So, dynamic loading can help to ease this restriction, but generally requires special precautions and extra work by the programmer. So, the requirement that instructions must be in physical memory to be executed seems both necessary and reasonable, but it is also unfortunate since it limits the size of a program to the size of the physical memory. So in fact, an examination of real programs show us that in many cases, the entire program is not needed. For instance, consider the following. So, programs often have code to handle unusual error conditions. Since these errors seldom, if ever, occur in practice, this code is almost never executed. So, arrays, lists, and tables are often allocated more memory than they actually needed. So an array may be declared 100 by 100 elements, even though it is seldom larger than 10 by 10 elements. An assembler symbol table may have room for 3,000 symbols. So although the average program has less than 200 symbols. So certain options and features of a program may be used rarely. For instance, the routines on US government computers that balance the budget have not been used in many years. So, even in those cases where the entire program is needed, it may not all be needed at the same time. So, the ability to execute a program that is only partially in memory would confer many benefits. So, a program would no longer be constrained by the amount of physical memory that is available. Users would be able to write programs for an extremely large virtual address space, simplifying the programming task. So because each user program could take less physical memory, more programs could be run at the same time with a corresponding increase in CPU utilization and throughput but with no increase in response time or turnaround time. So less input output would be needed to load or swap user programs into memory. So each user program would run faster. So thus running a program that is not entirely in memory would benefit both the system and the user. So virtual memory involves the separation of logical memory as perceived by users from a physical memory. This separation allows an extremely large virtual memory to be provided for programmers when only smaller physical memory is available. So, ito po yung sa physical memory po natin. So, this diagram showing virtual memory that is larger than physical memory. So, virtual memory makes the task programming amount of physical memory available. She can concentrate instead on the problem to be programmed. So, the virtual space of a process refers to a logical or virtual view of how process is stored in memory. Typically, this view is that process begins at a certain logical addresses, says address 0 and exists to contiguous memory as shown in figure 2. So this is a virtual address space. Recall from chapter 8, though in fact, physical memory may be recognized in page frames and the physical page frames assigned to a process may not be contiguous. It is up to the Memory Management Unit or MMU to map logical pages to physical page frames in memory. So, note in figure 9.2 that we allow the heap to grow upward in memory as it is used for dynamic memory allocation. So similarly, we allow for the stack to grow downward in memory through successive function calls. The large blank space or hole between the heap and the stack is part of the virtual address. Our address space but will require actual physical page only if the heap or stack grows. So virtual address space that include holes are known as sparse address spaces. Using a sparse address space is beneficial because the holes can be filled as the stack or heap segments grow as we wish to dynamically link libraries or possibly other shared objects during program execution. So, in addition, uh, to separating logical memory from physical memory, virtual memory allows files and memory to be shared by two or more processes through page sharing. So, nasa section 8.5 po yan. This leads the following benefits. So, system libraries can be shared by several processes through mapping of the shared object into a virtual address space. Although each process considers the libraries to be part of it, virtual address space, the actual pages where the libraries reside in physical memory are shared by all the processes. Typically, a library is mapped read-only into the space of each process that is only linked with it. Pages can be shared during process with a fork system call, thus speeding up process creation. So similarly, process can share memory. Recall from chapter 3 that two or more processes can communicate through the use of shared memory. Virtual memory allows one processes to create a region of memory that it can share with another processes or another process. So processes sharing this region consider it part of their virtual address space. Yet, the actual physical pages of memory are shared, as is illustrated in figure 9.3. So, ito po siya. Shared library using the virtual memory. We further explore these and other benefits of virtual memory. Later in this chapter, first though, we discuss implementing the virtual through demand paging. So, demand paging, demand paging. So, consider how an executable program might be loaded from disk into memory. One option is to load the entire program in physical memory at program execution time. So, however, a problem with this approach is that we may not initially need the entire program in memory. Suppose a program starts with a list of available options from which the user is to select. Loading the entire program into memory results in loading the executable code for all options, regardless of whether or not an option is ultimately selected by the user. An alternative strategy is to load pages only as they are needed. So, this technique is known as the demand paging. So, and is commonly used in virtual memory systems. With demand page virtual memory, pages are loaded only when they are demanded during program execution. Pages that are never accessed are thus never loaded in physical memory. A demand paging system is similar to paging system with swapping. Yan po yung nasa figure 9.4 po natin. Where process reside secondary memory, usually a disk. So, when we want to execute process, we swap it into memory. So, rather than swapping the entire process into memory, though we use a lazy swapper. A lazy swapper never swaps a page into memory unless that page will be needed. In the context of a demand paging system, use of the term swapper is technically incorrect. A swapper manipulates entire processes, whereas a pager is concerned with the individual page or pages of a process. We thus use pager rather than swapper. So in connection with demand paging. So basic concepts. When a process is to be swapped or swapped in, the pager guesses which page will be used before the process is swapped out again. Instead of swapping in a whole process, the pager brings only those pages into memory. Thus, it avoids reading into memory pages that will not be used anyway. So, decreasing the swap time and the amount of physical memory needed. So, if the bit is set to invalid, the page either it is not valid, that is not in the logical address space of the process, or is valid but is currently on the disk. So, the page table entry for a page that is brought into memory is set as usual. But the page table entry for a page that is not currently in memory is and either simply marked invalid or contains the address of the page on this. So this situation is depicted in figure 9.5. So figure 9.5, page table when some pages are not in main memory. Notice that marking a page invalid will no effect if the process never attempts to access that page. So hence, if we guess right and page in all pages that are actually needed and only those pages, the process will run exactly as though we had brought in all pages. While the process executes and access pages that are memory resident or execution proceeds normally. But what happens if the process tries to access the page that was not brought into memory? So, access to a page marked invalid causes a page fault. So, the paging hardware, in translating the address through the page table, will notice that the invalid bit is set, causing a trap to the operating system. This trap is a result of the operating system's failure to bring the desired page into memory. So the procedure for handling this page is straightforward. So yan po yung nasa 9.6 natin, steps in handling a page fault. So we check an internal table, usually kept in the process control block, for this process to determine whether the reference was a valid or an invalid memory access. So if the reference was invalid, we terminate the process. If it was valid but we have not yet brought in that page, we now page it in. We find a tree frame by taking one from the free frame list. For example, we schedule a disk operation to read the desired page into a newly allocated frame. When the disk read is complete, we modify the internal table kept with the process and the pages table into indicate that the page is now in memory. So we restart the instruction that was interrupted by the trap. The process can now access the page as though it had always been in memory. So in the extreme case, we can start executing a process with no pages in memory. When the operating system sets the instruction pointer to the first instruction of the process, which is on a non-memory resident page. So the process immediately falls for the page. After this page is brought into memory, the process continues to execute, faulting as necessary until every page that is needs in memory. At that point, it can execute with no more faults. So this scheme is pure demand paging. Never bring a page into memory until it is required. So theoretically, Some programs could access several new pages of memory with each instruction execution. So one page for the instruction and many for data, possibly causing multiple pages or multiple page faults per instruction. So this situation would result in unacceptable system performance. Fortunately, analysis of running processes shows that this behavior is exceedingly unlikely. Programs tend to have a locality of reference, so described in section 9.61, which result in reasonable performance from demand paging. The hardware, the hardware to support demand paging is the same as the hardware for paging and swapping. So page table. This table has the ability to mark an entry invalid through a valid invalid bit or special value of protection bits. Secondary memory. This memory holds those pages that are not present in main memory. The secondary memory is usually a high-speed disk. It is known as the swap device, and the section of this used for this purpose is known as swap space. Swap space allocation is discussed in Chapter 10. A crucial requirement for demand paging is the ability to restart any instruction after a page fault because we save the state or registers condition codes instruction counter of the interrupted process when the page fault occurs. We must be able to restart the process in exactly the same place and state, except that its desired page is now in memory and is accessible or accessible. In most cases, this requirement is easy to meet. So a page fault may occur at any memory reference. If the page fault occurs on the instruction fetch, we can restart by fetching the instruction again. If a page fault occurs while we are fetching an operand, we must fetch and decode the instruction again and then fetch the operand. As a worst case example, consider a three address instructions as such as ADD, the content of A to B, placing the result in C. So these are the steps to execute this instruction. So the first one is to fetch and decode the instruction. So yun po yung ADD. So fetch A, fetch B, and add mo po yung na-fetch mo na A and B, store the sum in C. If we fault when we try to store in C, so because C is in a page not currently in memory, we will have to get a desired page. Bring it in, correct the page table, and restart the instruction. The restart will require fetching the instruction again, decoding it again, fetching the two operands again, and then adding again. So the major difficulty arises when instructions may modify several different locations. For example, consider the IBM system, so 360 by 370 MVC or move character instructions, which can be moved up to 256 bytes from one location to another, possibly overlapping location. If either block or source or destination straddles a page boundary, a page fault might occur after the move is partially done. In addition, if the source and destination blocks overlap, the source block may have been modified, in which case we cannot simply restart the instruction. So this problem can be solved in two different ways. In one solution, the microcode computes and attempts to access both ends and both blocks. If a page fault is going to occur, it will happen at this step before anything is modified. The move can then take place. So we know that no page fault can occur since all the relevant pages are in memory. So other solutions uses temporary register to hold the values of overwritten location. If there is a page fault, all the old values are written back into memory. before the trap occurs. This action restores memory to its state before the instruction was started so that the instruction can be repeated. This is by no means the only architectural problems resulting from adding paging to an existing architecture to allow demand paging, but it illustrates some of the difficulties involved. Paging is added between the CPU and the memory in a computer system. It should be entirely transparent to the user process. Thus, people often assume that paging can be added to any system, although this assumption is true for a non-demand paging environment. So, where a page fault represents a fatal error, it is not true where a page fault means only that an additional page must be brought into memory and the process restarted. Performance of demand paging. Demand paging can significantly affect the performance of a computer system. To see why, let's compute the effective access time for a demand page memory. For most computer systems, the memory access time denoted demand paging can significantly affect the performance of a computer system. To see why, let's compute the effective access time for a demand page memory. For most computer systems, the memory access time denoted MA or ranges from 10 to 200 nanoseconds. As long as we have no page faults, the effective access time is equal to the memory access time. If, however, a page fault occurs, we must first read the relevant page from this and then access the desired word. So, let P the probability of a page fault. 0 is less than or equal to P less than or equal to 1. We would expect P to be close to 0. That is, we would expect to have only a few page faults. The effective access time is then effective access time equal to 1 minus P multiplied by MA plus P multiply page fault time. To compute the effective access time, we must know how much time is needed to service a page fault. So a page fault causes the following sequence to occur. So first one is to trap the operating system. Second one is the save the user registers and process state. Determine that the interrupt was a page fault. Check that the page reference was legal and determine the location of the page on the disk. So, issue a read from the disk to a free frame. So, wait a queue for this device until the read request is serviced. So, wait for the device seek and or latency time. Begin the transfer of the page to a free frame. So, while waiting, allocate the CPU to some other user or CPU scheduling. So, receive an interrupt from the disk input-output subsystem. So, save the registers and process state for the other user. So, determine that the interrupt was from the disk. Correct the page table and other tables to show that the desired page is now in memory. Wait for the CPU to be allocated to this process again. So restore the user's registers, process state, and new page table, and then resume the interrupted instruction. Not all these steps are necessary in every cases or in every case. For example, we are assuming that in step 6, so may step 6 na rin. The CPU is allocated to another process while input-output occurs. This arrange allows multi-programming to maintain CPU utilization, but requires additional time to resume the page fault service routine when the input-output transfer is complete. So in any case, we are faced the three major components of page fault service time. So number one is the page fault interrupt, read in the page, and restart the process. So the first and third task can be reduced with careful coding the several hundred instructions. So the first and third task can be reduced with careful coding to several hundred instructions. This task may take from 1 to 100 microseconds each. So the page switch time, however, will probably be close to 8 milliseconds. A typical hard disk has an average latency of 3 milliseconds, a seek of 5 milliseconds, and a transfer of 0.05 milliseconds. Thus, the total paging time is about 8 milliseconds, including hardware and software time. So remember also that we are looking at the only device service time. If a queue of processes is waiting for the device, we have to add device queuing time as we wait for the paging device to be free to service our request, increasing even more the time to swap. With an average page fault service time in 8 milliseconds and a memory access time of 200 nanoseconds, the effective access time in nanosecond is effective access time is so with an average page fault service time of 8 milliseconds and a memory access time of 200 nanoseconds, the effective access time in nanosecond is effective access time equal to 1 minus p multiplied by 200 which is our nanoseconds and plus p which are yun po yung probability natin 8 milliseconds. Yan po yung ating formula. So we see that the effective access time is directly proportional to the page fall rate. If one access out of 1,000 causes a page fault, the effective access time is 8.2 microseconds. So the computer will be slowed down by a factor of 40 because the demand paging. We see then we see then that the effective access time is directly proportional to the page fall rate. If one access is out of 1,000 causes a page fault, the effective access time is 8.2 microseconds. The computer will be slowed down by a factor of 40 because of demand paging. So if you want performance degradation to be less than 10%, we need to keep the probability of page faults at the following level. So ito po siya. An additional aspect of demand paging is the handling and overall use of swap space D or swap space. This input-output to swap space is generally faster than that the file system. It is a faster file system because swap space is allocated in much larger blocks, and file lookups and indirect allocation methods are not used. An additional aspect of demand paging, the system can therefore gain better paging throughput by copying an entire file image into the swap space at process start up, then performing demand paging from the swap space. Another option is to demand pages from the file system initially, but no write uh, or but to write the pages to swap space as they are replaced. This approach will ensure that only needed pages are read from the file system, but that all subsequent paging is done from swap space. Copy on write. So in section 9.2, we illustrated how a process can start quickly by demand paging in the page containing the first instruction. So however, process creation using the fork system can or system call may initially bypass the need for the paging by using a technique similar to page sharing. So that is covered in section 8.5.4. This technique provides rapid process creation and minimizes the other or the number of new pages that must be allocated in the newly created process. So recall that the fork system call creates a child process that is a duplicate of its parent. So traditionally, fork work by creating a copy of the parent's address space for the child, duplicating the pages belonging to the parent. So however, Considering that many child processes invoke the exec function, system call immediately after creation. The copying of the parent's address space may be unnecessary. So instead, we can use a technique known as a copy on write, which works by allowing the parent and a child processes initially to share the same pages. So these shared pages are marked as copy on write pages, meaning that if either processes writes to a shared page, a copy of the shared page is created. Copy on write is illustrated in figure 9.7 and 9.8, which show the contents of the physical memory before and after process 1 modifies page C. So ito po yung figure 9.7 natin. Before process 1 modifies page C. And ito naman po yung figure 9.8 natin, which is the after processes 1 modifies page C. So makikita po natin yung difference nito sa sa physical memory na nadagdagan po siya ng copy of page C. Kaya naging dalawa po yung page C po natin sa physical memory. So operating system typically allocate these pages using a technique known as a zero fill on demand. So zero fill on demand pages have been zero out before being allocated, thus erasing the previous contents. So several versions of Unix, or including Solaris and Linux, provide a variation of the fork function system called vfork. So yun po yung sa virtual memory fork that operates differently from fork function with copy on write. So with vfork function, the parent process is suspended and the child processes uses the address space of the parent. So because vfork function does not use copy on write, if the child process changes any pages of the parent's address space, the altered pages will be visible to the parent once it resumes. So therefore, defer function must be used with caution to ensure that the child process does not modify the address space of the parent. So vfork function is intended to be used when the child process calls exec function immediately after creation, because no copying of pages takes place. Vfork function is an extremely efficient method of process creation and is sometimes used to implement Unix command line shell interfaces. So, yung next topic po natin is i-report po ng ating kagrupo.
I'm from Ervie Tattao. So let's proceed to the next page, which is the page replacement. So in our early discussion of the page fault rate, we assume that each page faults at most once when it is first reference. This representation is not strictly accurate. However, if a process of 10 pages actually uses only half of them, then demand paging saves an IO necessary to load the 5 pages that are never used. Um, so we could also increase our degree of multi-programming by running twice as many process. And thus, if we need 40 frames, we could run 8 processes rather than the the fourth that rather than the 4 could run if each requires 10 frames, 5 of which were never used. And if we increase our degree of multi-programming, we are over allocating our memory. So next is the need for the page replacement. So it can increase the um, strain on the memory placement algorithms, deciding how much memory to allocate to I/O and how much the program pages is significant challenge. So some system allocate a fixed percentage of memory for I/O buffers, whereas other al- others allows both user processes and the IO subsystem to complete for all the system memory. Over allocation of memory manifests itself as follows. So while user processes is executing a page, fault occurs. The operating system determines where the desired pages is residing on the disk, but then finds that there are no frames on the free frame rather, and all memory is used in the figure that this is showing. So next is the basic page replacement. So page replacement takes the following approach. If no frame is free, we find one that is only currently being used and free it. We can free a frame by writing its contents to subspace and changing the page tablet. So as you can see in the figure, and it indicates that the pages are no longer in the memory. As you, in this figure, we can also use the free frame to hold the page for which the process is faulted. We modify the page fault service to routine the include page replacement. So we have four. So first is the find the location of the desired page on the disk. So second is find the free frame, and third is the read the desired page into the newly free frame and change the page and the frame tables. And the fourth one is the continue the user process from where the page fault occurred. So notice that if no free free if no free frames are free, two pages transfer and one out and one in. And this situation effectively doubles the page fault service time and increases the effectiveness access in time accordingly. So next, the graph of page faults versus the number of frames. So to determine the number of page faults for a particular reference string and page replacement algorithm, we can also need to know the number of page frames available. So as you can see in the figure, obviously as the number of frames available increases, the number of page faults decreases. And for the reference string, consider that previously, for example, if we had three or more frames, we should have a only three faults and one fault for the first reference to each page. It contrasts with only one frame available. We would have a replacement with every reference, resulting in 11 faults in general, and we expect a curve such as in the figure that we see. So next, the FIFO page replacement. The simplest page replacement algorithm is the first in and first out. And a FIFO replacement algorithm associates with each page the time when that page was bought into memory. So as you can see in the figure, um, when a page must be replaced, the oldest page is chosen. So notice that it is no strictly necessary to record the time when a page is bought in. We can create a FIFO queue to hold all the pages in memory. We replace the page at the head of the queue, and when a page is bought into memory, we insert a tail of the queue. For our example is reference string are three frames are initially empty. The first three references, example is 7, 0, and 1, because the page faults are brought into the empty empty frames. So the next reference 2 replaces page 7, because page 7 was brought into the first, since 0 is the next reference and 0 is already in memory. We have no fault for this reference. So next is the optimal page replacement algorithm. And one of the discovery of Belady's anomaly was search for an optimal page replacement algorithm, and unfortunately the optimal page replacement algorithm is difficult to implement because it requires future knowledge of the reference string. So as you can see in the two figures, the number of frames and the page frames. So the algorithm that has the lowest page fault rate of the algorithms, and will never suffer from the Belady's anomaly. Such an algorithm does exist and has have been called OPT, or the MIN. It is simply this that replace the page that will not be used for the longest periods of time. Use of this page replace um, an algorithm guarantees that the lowest possible page fault rate for a fixed number of frames. So for example, on our sample reference, the figure, the first figure, um, the second figure, the optimal page replacement algorithm would yield the 9 page faults as shown in the figure number 2. And the first 3 references cause faults that fill in the 3 empty frames. And the reference to page 2 replace the page 7, because page 7 will not able to use until the reference 18, whereas page 0 will be used at 5, and page 1 at 14. So the reference to page 3 places the page again with only the 9 page faults. So optimal replacement is much better than the FIFO algorithm, which results a 15 faults. If we ignore the first 3, which all algorithms must suffer, then the optimal replacement is twice as good as FIFO replacement. In fact, no replacement algorithm can process this reference string in 3 frames with fewer than the 9 faults. So next is the LRU page replacement. If the optimal algorithm is not feasible, perhaps an approximation of the optimal algorithm is possible. So the key this distinction between FIFO and OPT algorithms, other than looking backward versus forward in time, is the FIFO algorithm uses the time when a page was brought into memory, whereas the OPT algorithm uses the time when a page is to be used. If we use a recent past as an approximation of the near future, then we can replace the page but that has not been used for the longest period of time. This approach is used in the least recent use algorithm, which is the LRU. So next is the stack. Other approach to implementing LRU replacement is to keep a stack of a page number. So as you can see in the figure, whenever a page is referenced, it is removed from the stack and put on the top. And in this way, the most recently used page is always at the top of the stack, and at least recently used page is always at the bottom of the stack. Because entries must be removed from the middle of the stack, it is the best implement in this approach by using double linked list with a head pointer and a tail pointer, removing a page and putting it on the top of the stack then requires changing 6 pointers outwards. So this is the second chance algorithm. The basic algorithm of second chance replacement is a FIFO replacement algorithm. So when a page, as you can see in the figure, when a page has been selected, however, we inspect its references bit. If the value is 0, we proceed to the replace. We proceed to replace this page. But if the reference bit itself set into 1, we give the page a second chance to move on the selected to select the next FIFO page. And when a page gets second chance, its reference bit is cleared and its arrival time is to reset to the current time. Thus, a page is given a second chance will not be replaced until all the other pages have been replaced or given. Next topic is the allocation of frames. So first is what is allocation of frames. So frame allocation algorithms are used if you have a multiple processes. It helps decide how many frames to allocate of to each process. There are various constraints to the strategies for the allocation of frames. You cannot allocate more than the total number of available frames. So there are many variations of this simple strategy. You can record that the operating system allocate all its buffer and table space from the free frame list. So when this space is not used by the operating system, it can be used to support user paging. So we can try to keep 3 free frames reserved on the free frame list at all times. Thus, when a page is fault occurs, there is a free frame available to which it is be written to the disk as the user process continues to execute. Other variants are also possible, but the basic strategy is clear. The user process is allocate any free frame. So next, the minimum number of frames. So our strategy for the allocation of frames are constrained in various ways. So we cannot, for example, allocate more than the total number of available frames unless there is a page sharing. So we must also allocate at least a minimum number of frames. Here, we look more closely at the later requirement. So one reason for allocating at least a minimum number of frames involves performance. Obviously, as the number of frames allocated to each process and decrease the page fault rate, increases slowing process execution. In addition, remember that when a page fault occurs before an executing instruction is complete, the instruction must be restarted. Consequently, we have we must have enough frames to hold the different page that any single instruction can reference. So, for example, consider a machine in which all the memory reference instruction may reference only one memory address. Allocation algorithms. The easiest way to split M frames among N processes is to give everyone an equal share. MN frames, ignoring frames needed by the operating system for the moment. And so, for instance, if there are 92 frames and 5 processes, each processes will get 18 frames. So the 3 leftover frames can be used as the free frame buffer pool. This this scheme is called an equal allocation. An alternative is to recognize that the various processes will need different amounts of memory. Consider a system with a 1 KB frame size. If a small student processes 10 KB and an alternative database of 127 KB are the only two processes running in the system with 62 frames, and it does not make much sense to give each process 31 frames. So the student process does not need more than 10 frames. So the other 21 are strictly speaking wasted. So next is the global versus local allocation. So other important factor in the way frames are allocated to the various processes is page replacement. So with multiple processes competing for frames, we can classify page replacement algorithms into two broad categories: global replacement and the um, local replacement. So global replacement allows a process to select a replacement frame from the set of all frames. So even the frame is currently allocated to some other process, that is one process can take a frame from other. So local replacement requires that each process select from only its own set of allocated frames. So next is the non-uniform memory access. So thus far in our coverage of virtual memory, we have assumed that all main memory is created equal, or at least that it is accessed equally. So on many computer systems, that is not the case. Often it's in system with multiple CPUs. A given CPU can access some section of main memory faster than it can access the others. So these performance difference are caused by how CPUs and memory are interconnected in the system. So frequently, such as system made of several system boards, each containing multiple CPUs and some memory. So the system boards can interconnected in various ways, ranging from the system buses to high-speed network connection like InfiniBand. So that's all. Thank you.
Trashing. Trashing. If a process does not have enough pages, the page fault rate is very high. This leads to low CPU utilization. So that means low CPU usage represent a low percentage of the amount of time to process a given set of tasks at a given period. For example, low utilization rate. As such, low CPU utilization is an indicator of inadequate computing resource management. So OS thinks that it need to increase the degree of multi-programming. Another process added to the system. A process is busy swapping pages in and out. So CPU utilization. So as you can see, tataas po siya and then bigla pong bababa po. Then demand paging and trashing. Why does demand paging work? So demand paging is a process in which data is moved from secondary memory to RAM, kung saan lahat ng data is not stored in the main memory because the space is limited in RAM. So, locality model. Process migrate from one locality to another. Localities may overlap. Why does trashing occur? So, trashing occurs when there are too many pages in memory and each page refers to another page. The real memory shortens in capacity to have all the pages in it, so it uses virtual memory. Working set model. So working set window, a fixed number of page references. WSS or Window SharePoint Services. The total number of pages reference is the most recent. D is equal to sum WSS equal total demand frames. So if D greater than M, right arrow trashing. Policy if D greater than M, then suspend one of the process. Page reference table. So meron po tayong nakikita dyan na window SharePoint po sa baba. Then T1 is equal to 1, 2, 5, 6, 7. Then sa kabila po is meron po tayong 3 and 4. Establish acceptable page fault rate. If actual rate too low, process loses frame. If actual rate too high, process gains frame. So, page fault rate, number of frames. So, increase number of frames, upper bound. Lower bound, decrease number of frames. Memory map file. Memory map file or I/O allows file I/O to be treated as routine memory access by mapping a disk block to page in memory. Simplifies file access by treating file I/O through memory rather than read and write system. A file is initially read using demand paging. A page size portion of the file is read from the file system into a physical page. Also allows several processes to map the same file, allowing the pages in memory to memory map files. So as you can see po, meron pong process A virtual memory, process B virtual memory, then this file. So multiple process may be allowed to map the same file concurrently to allow sharing of data. Write by any of the process, modify the data in virtual memory and can be seen by all others than map the same section of the file. So, memory map file, and then process 2. So, under this scenario, process can communicate using shared memory by having the communicating processes memory map the same file into their virtual address space. Allocating kernel memory. Treated differently from user memory, often allocated from a memory pool. So kernel requests memory for structures of varying sizes. Some kernel memory needs to be contiguous. Body system allocator. Allocate memory can fix size segment consisting of physically contiguous pages. Memory allocated using power of -2 allocator. Satisfies requests in unit size as power of 2. Requests rounded up to the next highest power of 2. Current chunk split into 2 bodies of next lower of 2. So, physically contiguous pages. So, nakikita po natin meron po siyang 256 KB. Then, kung mapapansin po natin is pababa po siya ng pababa into 128 KB, then 64 KB, then last is 32 KB. Slab is one or more physically contiguous page. Cache consists or more slabs, single cache or each unique kernel data structure. When cache created filled with objects marked as free, when structure stored object marked as use. So, kernel objects, meron pong tatlo, kernel objects, caches, and slabs. So, physically contiguous pages, kung mapapansin po natin ay can communicate using shared memory by having the communicating. So, yun lamang po.
Prepaging to reduce the large number of page faults that occurs. For instance, when a swap-out process is restarted, all its pages are on the disk, and each must be brought in by its own page fault. Prepage all or some of the pages a process will need before they are referenced. In a system using the working set model, for example, we could keep with each process a list of the pages in its working set. If we must suspend the process, we remember the working set for that process. When the process is to be resumed, we automatically bring back into memory its entire working set before restarting the process. If prepared pages are unused, I/O and memory was wasted. Prepaging may offer an advantage in some cases. The question is simply whether the cost of using prepaging is less than the cost of servicing the corresponding page faults. It may well be the case that many of the pages brought back into memory by prepaging will not be used. Page size. Page size selection must taken into consideration. First one is fragmentation. Memory is better utilized with smaller pages. However, if a process is allocated memory starting at location 0 and continuing until it has as much as it needs, it probably will not end exactly on a page boundary. Thus, a part of the final page must be allocated because pages are the units of allocation but will be unused. To minimize internal fragmentation, then we need a small page size. The next one is table size. For a given virtual memory space, decreasing the page size increases the number of pages and hence the size of the page table. For a virtual memory of 4 MB, for example, there would be 4096 pages of 1024 bytes, but only 512 pages of 8192 bytes. Because each active process must have its own copy of the page table, a large page size is desirable. The next one is the I/O overhead. I/O time is composed of seek, latency, and transfer times. Transfer time is proportional to the amount transferred, a fact that would seem to argue for a small page size. A desire to minimize I/O time argues for a larger page size. The last one is the locality. With a smaller page size, though total I/O should be reduced since locality will be improved. A smaller page size allows each page to match program locality more accurately. TLB reach, the amount of memory accessible from the TLB, and is simply the number of entries multiplied by the page size. The working set of each process is stored in the TLB, otherwise there is a high degree of page faults. Increase the page size. Another approach for increasing the TLB reach is to either increase the size of the page or provide multiple page sizes. If we increase the page size from 8 KB to 32 KB, we quadruple the TLB reach. However, this may lead to an increase in fragmentation for some applications that do not require such a larger page size. Provide multiple page size. Providing support for multiple page sizes requires the operating system to manage the TLB. Inverted page table. To reduce the amount of physical memory needed to track virtual to physical address translations. For the information to be available, an external page table must be kept. Inverted page table reduce the amount of physical memory needed to store this information. However, the inverted page table no longer contains complete information about the logical address space of a process, and that information is required if a reference page is not currently in memory. Program structure. Demand paging is designed to be transparent to the user program. Let's look at the example. Assume that pages are 128 words in size. Consider a C program whose function is to initialize to 0 each element of a 128 by 128 array. Notice that the array is stored row major. For pages of 128 words, each row takes one page. Thus, the preceding code zeros one word in each page, then another word in each page, and so on. If the operating system allocates fewer than 128 frames to the entire program, then its execution will result in 128 times 128 is equal to 16,384 page faults. In contrast, suppose we change the code to zeros all the words on one page before starting the next page, reducing the number of page faults to 128. Careful selection of data structures and programming structures can increase locality and hence lower the page fault rate and the number of pages in the working set. For example, a stack has good locality since access is always made to the top. A hash table, in contrast, is designed to scatter references, producing bad locality. Locality of reference is just one measure of the efficiency of the use of a data structure. System performance can be improved if the user has an awareness of the underlying demand paging. I/O interlock and page locking. One such situation occurs when I/O is done or from user virtual memory. I/O is often implemented by a separate I/O processor. For example, a controller for a USB storage device is generally given the number of bytes to transfer and a memory address for the buffer. When the transfer is complete, the CPU is interrupted. Operating system examples. Windows. Windows implements virtual memory using demand paging with clustering. Clustering handles page faults by bringing in not only the faulting page but also several pages following the faulting page. Processes are assigned working set minimum and working set maximum. The working set minimum is the minimum number of pages the process is guaranteed to have in memory. If sufficient memory is available, a process may be assigned as many pages as its working set maximum. Automatic working set trimming is performed to restore the amount of free memory. When the amount of free memory falls below the threshold, the virtual memory manager uses a tactic known as automatic working set trimming to restore the value above the threshold. Automatic working set trimming works by evaluating the number of pages allocated to processes. If a process has been allocated more pages than its working set minimum, the virtual memory manager removes pages until the process reaches its working set minimum. Solaris maintains a list of free pages to assign faulting processes. When a thread incurs a page fault, the kernel assigns a page to the faulting thread from the list of free pages it maintains. Lots free represents a threshold parameter amount of free memory to begin paging. Test free represents a threshold parameter to increase paging. Min free represents a threshold parameter to begin swapping. Paging is performed by page out processes. Page out scans pages using modified clock algorithm. Scan rate is the rate at which pages are scanned. Virtual memory is commonly implemented by demand paging. Pure demand paging never brings in a page until that page is referenced. The first reference causes a page fault to the operating system. The operating system kernel consults an internal table to determine where the page is allocated on the backing store. The page table is updated to reflect this change and the instruction that caused the page fault is restarted. This approach allows a process to run even though its entire memory image is not in main memory as page replacement algorithms are used. FIFO page replacement is easy to program but suffers from anomaly. Optimal page replacement requires future knowledge. LRU replacement is an approximation of optimal page replacement, but even it may be difficult to implement. Most page replacement algorithms, such as the second chance algorithm, are approximations of LRU replacement. In addition to requiring us to solve the major problems of page replacement and frame allocation, the proper design of a paging system requires that we consider prepaging, page size, TLB reach, inverted page tables, program structure, IO interlock and page locking, and other issues.